Welcome everyone. This is the course on X-ray and microanalysis in the scanning electron microscope. It's the follow-on course from the SEM imaging course you should all have completed by now. Why do we need to do a separate course about microanalysis? I think that the critical point to understand here is quality control. If you look at the image on the left, and I were to ask you, even with hardly any training on SEM, is that a good or a bad image? Most people would answer, yes, it's a good image. And the reason is, it's well focused, it's got good depth of field, good brightness contrast. You can tell that's a good image, even without really knowing much about it, by the fact that it's not a blurry, bad image. Yet, if I ask you, that spectrum to the right, which is microanalysis, X-ray microanalysis, which gives elemental information about the specimen, the reason we're here, to find out the composition of our specimen. If I point to that spectrum and I ask you, is it a good spectrum? It's a much harder question to analyse, because the computer, by default, always produces an in-focus output. It's no longer that the normal image view is a quality check. You've now got to understand the fundamentals of how analysis is performed, and then did you design a good experiment? Quality in analysis usually comes from the beginning, moving it forward so that you trust the result, as opposed to looking at the result at the end and saying, yes, that's a publication, quality image I can use. I myself keep a lot of images that in the end I decide not to use. They're not good enough. Yet I see people in microanalysis often keeping spectra which I wouldn't trust, yet they don't know not to trust it. So it's all about quality control. And for those who care, yes, there is an error in that spectrum, and it's very hard to pick, and most people wouldn't have picked it. Okay, so before I start, I'm going to use some language here, and I just want to make sure that we're familiar with all the language we're going to be using. So, I will talk about energy. What is energy? Energy is the ability to perform work on an object or heat a system. We often won't be talking about systems too much because they're much more macroscopic, and we'll be working mostly at the atomic level. Energy is measured in joules. You would all know this from high school. Voltage, or electric potential, is the work or energy needed to move a charge. So voltage is energy per unit charge, and in particular, 1 volt is 1 joule per coulomb. Given that definition of what a volt is and what voltage is, it's pretty obvious that a voltage times a charge equals energy. So for us, we'll use the electron volt as our unit of energy. Why? Because it's much more natural to the scale we'll be working at. 1 electron volt is the energy produced by the charge of 1 electron raised to the potential of 1 volt. And in joules, it is 1.602 by 10 to the minus 19 joules. It's a very, very small unit of energy, but it's very useful for the scale we'll be working at the atomic level in a scanning electron microscope, an SEM. In particular, the mathematics now becomes very, very simple. Macroscopically, the SEM might have, for example, an accelerating voltage of 20 kV, 20,000 volts. But that means microscopically, each electron has an individual energy of 20 keV. So we can convert from the macroscopic to the microscopic by just putting a little e in there. So it's a very useful unit of energy for our purposes. I'll also talk a bit about scattering. And for those who can't remember, elastic scattering is when the primary particle keeps its energy and doesn't give energy to the system. So that's called an elastic scattering event. We say energy is conserved. In an inelastic scattering event, the primary particle imparts some of its energy to the system, the surrounding material. And so we say that energy is not conserved. And usually, when the energy is not conserved and energy has gone to the system, the surrounding particles, we cause some event to happen, and we're interested in what that event will be. We'll start at the beginning. Electron beam and sample interaction. People sometimes get confused in X-ray microanalysis, and I think they get too involved at the the interface of the software and the settings and stuff like that. And certainly you need to know that, but I always like to start at the fundamentals and then build my way up from the basics to how the system should be operated. So let's never lose track of the fundamentals. The fundamentals are we are throwing electrons at atoms. That's what we're doing. The electrons come from the SEM, and we can adjust the electron beam by adjusting the SEM controls, and the atoms are the specimen atoms. We don't have much control on that because that is what we're looking at. The one way I need to point out where we do have control is cleanliness. You need to get information from the atoms that are representative of your sample. So in particular, if you have contamination on the surface of your sample, that's where a lot of your information will be coming from. So the step one in good analysis is give me a clean specimen. If you've touched it with your hands, you have finger grease on it. We often wear gloves, rinse things in ethanol, but it's also very important to keep your gloves clean. If you've got gloves on and you say, scratch your hair or you use your phone, you've probably contaminated your gloves. So we need to keep the specimen clean. The higher the quality analysis, the higher the quality cleanliness of a specimen I expect from you. But electrons and atoms, that's our fundamental. The next big step forward is we need to understand the scale of how we're working. The electron beam is hitting my specimen, and the electron beam might be coming down at the nanoscale, say 2 nanometers diameter. That would be a typical electron beam diameter in a field emission electron microscope. So 2 nanometer beam coming down, but then it hits the specimens and the electron beam begins to scatter off the atoms, and it produces an interaction volume. The scale of that volume is important to us. The first signal we're going to talk about is the secondary electron signal. That's a surface signal. Secondary electrons are weak, low energy electrons, and they only escape from the surface of the material. These values are all rough because it depends on the exact material and exactly what you're doing, but typically you could assume that most of the secondary electrons would be generated in the top 5 nanometers of your specimen. They will produce edge effect or give us good shape information. So secondaries are very good for seeing the shape of your specimen. Next is backscattered electrons. These are called BSEs or comp electrons because comp stands for composition. And what they give is atomic number contrast. They're a much deeper signal because whereas the secondary electrons are weak electrons, low energy, inelastically scattered, the backscattered electrons are high energy electrons that are elastically scattered. They should come out at roughly the same energy of the beam. They would penetrate hundreds of nanometers into the specimen and the signal would be seen from that depth. Remember, atomic number is the symbol Z, and that's the number of protons that an element has. Hydrogen 1, helium 2, lithium 3. So what we see with backscatter is atomic number contrast. The periodic table is ordered on Z number, on atomic number. So the higher up the periodic table the atom is, the brighter the signal will be. So with secondaries, we see shape information, but with backscatters, we're effectively seeing chemical contrast. And that's a very, very useful and important signal to us, but it's a deeper signal. And finally, where we'll spend a lot of our time talking about is over the whole interaction volume, from the top to the bottom, we'll be producing X-rays. These X-rays and the measuring of the X-ray energy or wavelength is what we would term X-ray microanalysis. Because the electron beam stimulates these X-rays, the measuring of these X-rays will give us the elemental composition of the material within the interaction volume. And how big is the interaction volume? It depends on the accelerating voltage of the SEM, it depends on the specimen itself, but in general, we can make the assumption that it's usually 1 to 2 microns in size. This is a very important consideration. The beam itself is coming down at 2 nanometers, yet the interaction volume is 2 microns. So each signal comes from a different volume, and that affects the resolution. Yes, scanning electron microscopes have nanometer resolution, but typically, unless you're doing something very tricky, typically that is using the secondary electron signal which comes from the top few nanometers and gives us shape information. As soon as we want to do analysis, even though the beam diameter is still the same, we're now analysing from a greater scattered volume. We're suddenly doing microanalysis at the micron scale. Notice it's called microanalysis, it's not called nanoanalysis. That's one of the things you need to know is you shouldn't analyse anything too small because you're now getting information from multiple different materials. Scale is very important. We've got two electron signals, the secondary signal and the backscatter signal. So the question is, why two signals? Well, the reason is, you've got basically the atom is divided into two parts, the electron cloud and the nucleus. And we get inelastic scattering from the electron cloud, and we get elastic scattering from the nucleus. And these inelastic scattered electrons are called secondary electrons, while the elastic scattered electrons are called backscattered electrons. And we've drawn a bit of a diagram, but basically the electron beam interacts with the electron cloud and would eject an atomic electron from the specimen. This is important. Secondary electrons generally actually come from the specimen, usually valence shell electrons. The high energy primary beam from the SEM will knock out and impart a little bit of energy into a valence electron, and that will be ejected and that will become a secondary electron. We've drawn a diagram to show that. Realistically, that angle of deviation is quite high. Most secondary electron angular deviations, the primary beam would vary by less than a degree. Now, if we considered, again, an atom, you've got electrons around it, a positive core. The electron, the primary beam electron from the SEM, is attracted to the atomic nucleus. It does an orbit round it, and then it goes back out. Secondary electrons are from the specimen, backscatter electrons are from the SEM. Secondary electrons are weak, inelastically scattered electrons. Backscattered electrons are high energy, elastically scattered electrons. A backscattered electron can go anywhere from 0 to 180 degrees. 180 is quite rare, but again, it can go through much higher angular deviations than a secondary electron. Let's talk more about secondary electrons. They are produced by inelastic scattering from the atoms, from the electron cloud. We've talked about that. They are low energy electrons, come from the specimens, less than 50 eV in energy. They give much more surface information, typically come from the top 5 nanometers. The actual value is statistical and specimen dependent, but that's a good working value for us to start with. They provide contrast due to edge effect. Edges are bright. When you see a digital image, it's made of pixels, some are dark, some are bright. The question is, why is that pixel bright, why is that pixel dark? In secondary electrons, it's because edges are bright, the edge effect. Why are edges bright? Because with sharp features, there's a greater surface area for these secondary electrons to escape from. I'll show you that in a second, but I'd just like to point out we have two types of secondary electrons. SE type 1s, which are secondary electrons created by the primary beam, a high energy beam, but the backscattered electron is also a high energy beam as it goes out of the specimen, and as the backscatter electron beam leaves the specimen, it can also create secondary electrons, and they're called SE type 2s. The SE type 1s are the higher resolution signal, the ones that we really want to use. Consider a material with some topography, and there's a specimen, and if you look at that dark blue line there, consider that to be the top 5 nanometers. Secondary electrons will only escape from that region. If I drop the beam on a flat surface, only a small amount of secondary electrons escape. But if I drop the beam on a sharp surface, there's a lot more area within 5 nanometers that the secondary electrons can escape from, therefore it's a brighter region. There's one more effect I need to quickly tell you about. You would remember this from high school, that if you've got a conductive sphere and you put a static electric charge on it, the electrons would move to be evenly distributed on the surface of the sphere. But you also might remember that if I got a conductive material that had a sharp end and a blunt end, and I put a static electric charge on it, the electrons would flow to the sharp end. And that still also happens in the SEM. Electrons, low energy secondary electrons, especially if the material is conductive, can begin to flow, and they will tend to flow to the sharp edges, and that's where they're more likely to jump off. This also adds to the contrast mechanism. For secondary electrons, it enhances the edge effect. Let's talk about backscatter electrons, or BSEs. It's also in some machines called comp mode, because comp stands for composition. Backscatter electrons are produced by elastic scattering from the nucleus. They are high energy electrons. They are from the primary beam. They are SEM beam electrons. They give deeper information, usually hundreds of nanometers. The actual value depends on the accelerating voltage of the SEM and the specimen material, but usually hundreds of nanometers. And they provide contrast based on atomic number. High Z is bright. Remember, Z, the atomic number, is the number of protons in the nucleus of the atom. The positive nucleus attracts the negative electron, and that causes the scattering effect. So more protons, more scattering, brighter image. So there's a low Z material on the left, and for example, carbon, if it has atomic number 6, it's been shown that at 10 kV, carbon has a backscatter yield of about 7%. So 7% of the primary beam would come back out as backscatter electrons. If you go to something that's much higher atomic number, here I've used the example of tin, which is Z equals 50. Again, at the same accelerating voltage, 10 kV, that has a backscatter yield of 41%. 41% of the primary SEM beam will come back out of the sample as backscattered electrons. Naturally, the high Z tin on the right will appear much brighter in the SEM than the low Z carbon on the left, simply because of their different backscatter yields. I need to point out one more subtle feature here. This is a good cross-section through an SEM. The blue horizontal surfaces at the top represent the backscatter detector. The backscatter detector is usually mounted above the specimen with a small hole for the beam to penetrate. The secondary electron detector, which is coloured green, is on the right, and they normally come in from the side. A backscatter detector is a high energy electron detector. It only measures high energy electrons, and so it will not see secondary electrons because they are too weak. Remember, secondary electrons have less than 50 eV in energy, whereas normally a backscatter electron would have keV in energy. Quite different. And backscatter electrons, they're high energy electrons with nominally the same energy as the primary beam. They travel fast and in straight lines. So you can see where the primary beam is hitting the specimen in red, and the backscatter electrons travel out in straight lines and hit the detector. Now, secondary electrons are different. They are weak, less than 50 eV in energy, and so my secondary electron detector off to the right here has in front of it a cage that has something like positive 200 or 300 volts on it, and that's called the collector bias. 200 or 300 volts has the ability to attract 50 eV electrons, but not the ability to attract 20 keV backscatter electrons. So this voltage is chosen to be above a typical SE volt energy, but below a typical BSE energy. So secondary electrons, which are weak, are attracted to this voltage and hit the detector. The good thing is, the ones that are on the right side of the mountain here get attracted to it. They're in green, but the ones that are on the left side of the mountain will actually go up and around and still hit the detector. The good thing about secondary electrons is, within reason, they will go around corners. And so you get to see all of the specimen as much as you can. Less so with backscatter electrons. The thing about my secondary electron detector is it's really just a low energy electron detector. And because it can measure low energy electrons, it can also measure high energy electrons. So it's not an SE only detector, it measures both SE and BSE electrons. It will see both secondaries and backscatters. So if you look at this backscatter electron here, this one is going to hit the detector, and that will be measured by the detector. But because backscatter electrons only travel in straight lines, The ones on the right will hit the secondary detector, the backscattered electrons on the right, but the ones on the left will move away from the detector. Basically, with a secondary detector, if you've got topography, one side will always appear brighter than the other side. That actually is very nice. It gives a three-dimensional effect to the image, but that brightness is due to the backscattered electrons. Let's have a look at some real images. This is a polished surface of a metal. It's aluminium alloy with copper in it. It's a flat polished specimen, but it's got porosity. So this is a hole in the surface, that big hole in the center. You can see in backscatter that there's some bright regions. They're all over the place. And they are the copper-rich regions. They're the high atomic number regions. And you can also see big grey regions where there is no brightness to it, and that is the region that's mostly aluminium. So straight away, we've got good atomic number contrast here. Any metallurgist could look at that image and straight away say that copper is on the grain boundaries. It's very easy to interpret because we know the elements that are being added to the metal alloy, and by knowing the different Zs, we can see how they segregate, and we can very quickly and easily interpret the image. The same image I'm now going to show you in secondary mode. See how the secondary electrons penetrate and can be removed from the hole, so I can sort of see around corners. Within reason, the big hole I can see inside, the small hole here to the right, not big enough to let out significant electrons, I don't really see it. You can see this edge of the hole is brighter than the opposite edge. It tells me that it's somewhere like between 12 and 1 o'clock is where my secondary electron detector is positioned. And that this brightness is due to direct backscatter electrons hitting my secondary electron detector. You can also see around the whole pore space or hole that there's a bright white edge. That is the edge effect we've talked about. We can see it clearly in this. If you go back to backscatter, you can find regions like here at say 10, 11 o'clock where you can see the edge of the hole and it's not bright. No edge effect in backscatter. Go to secondary, the whole edge is white due to edge effect. You can also notice in regions that we know to be copper rich because of our backscatter image, in secondary it's slightly brighter grey, just a little bit. That's the copper rich region producing more SE type 2s from the backscatter beam. So you don't often see SE type 2s directly, but you will on a polished surface when there is ample Z contrast there. Let's now move on to basic SEM operation. The SEM forms an image by scanning or rastering the electron beam over the sample surface. In the middle, I've got my sample, and those red dots are where the beam places itself to produce an image. At each one of those pixels will produce both secondary and backscatter electrons. Depending on which detector I'm using, I will form an image. On the left, that is my image. I basically put it together from the information I get from the raster. If I wanted to take a higher magnification image, it's simple. I just move those spots, the raster, closer together. And so now on the right, I get a magnified image. Magnification is through adjusting the raster of the beam. A typical SEM raster would be something like 1280 times 960 pixels, or really machine dependent. That's a variable you can adjust. The resolution limit is when the pixels get so close that neighbouring pixels begin to overlap each other. And that's when we're called spot size limited. So typically SEMs are optimised for the high magnification end, because at low magnification we have light as one of our tools. Light is good up to about 1,000 times with conventional optics. There are super resolution machines, but we're not going to talk about that. The SEM has certain limitations at low magnifications. The electron beam goes vertically down and hits the specimen. In an ideal world, as we raster the beam and we step it in our X by Y matrix of pixels, that beam would just move horizontally and then just drop down again and just keep dropping down vertically. It's very, very difficult to make a machine to keep the beam always perpendicular to the surface when doing a raster. What we tend to buy is a machine that deviates the beam via a certain fixed angle. And what the machine does when it's rastering is it tends to always step at a fixed angle. And you can see from this diagram here that the angle, theta 1, theta 2, theta 3, theta 4, is constant. But the step size on the surface, x1, x2, x3, x4, is going bigger and bigger and bigger. Now at higher magnifications, this error fades to nothing. This is when we get to the sine theta equals theta approximation, which you would have learnt at some stage. But at low magnification, this error is quite significant. How low is low? Well, it depends on how good you want your results to be. Once I'm at a few hundred times, I'm not worried about it. Below 100 times, I'm maybe a little bit concerned. Below 50 times, I'm probably very concerned. So the electron microscope, it's a powerful magnification tool, but it has a distortion at lower magnifications, in which case light is a better tool to use. If you're not too sure, I always recommend you put a reference material in there, a grid, a reference grid where you know its exact spacing, and just image it the way you would image your normal specimen and just check whether you've got any distortions. Most digital microscopes have a stage coordination X, Y, Z. If you happen to be trying to measure large distances, one of the things to do, rather than trust a very low magnification image, is move one feature to the centre of screen, note down its X, Y coordinate from the digital stage, then move another feature to the centre of screen, note down its XY coordinate from the digital stage, and then the distance between those two features is x1 minus x2, y1 minus y2. You can do simple mathematics with the digital stage. I do that quite a lot. Let's talk about the electron column. At the top, we've got the filament. This is our source of electron. Normally, we heat this up and we begin to boil for electrons. The electrons spray out in all directions, not very useful to us. Over the filament, we have this thing called a grid cap or a Vaynot assembly. It has a negative voltage or bias with respect to the filament, and that forces the electrons that are emitted to deviate away from it and focus themselves in the small hole in the centre. That is called the crossover point or the virtual source. This virtual source is then accelerated down the electron optics column from the anode. The anode has a positive voltage which attracts the electrons and gives them their forward speed. It energizes the beam and gives it the electrons their kinetic energy. So the energy of the beam comes from the anode, which you set with the accelerating voltage. We have the condenser lens. Now this can be a bit confusing because depending on if your machine is more about imaging, the control that would adjust the condenser lens may be called the spot size. If, however, you've got a microanalytical machine, such as a microprobe, which is similar but a little bit different, then this control that still controls the condenser lens is called the probe current or the beam current, something like that. The first lens focuses the virtual source to a crossover point, and this crossover point is filtered through the aperture. We can adjust this lens to produce a small spot or a large spot. Now, depending on what you want, it has different applications. A small spot is good for high resolution imaging, and it allows us to get the raster as close as possible for the maximum magnification. But a small spot has very few electrons in it. So for us doing X-ray analysis, the X-rays are created by the electrons. If we don't have many electrons, we don't have many X-rays to measure. So often for us, we go to a large spot, which decreases the fundamental resolution of the machine, but it gives us lots of electrons, lots of X-rays, and we can get some good spectral analysis happening. That is the bargain between resolution and signal. That's where a lot of the adjustment is made in the spot size, or the beam current, whichever way you want to call it. Once you've created your spot, and this is often then brought into focus with the final lens, which is called the objective lens. The objective lens is controlled with the focus control, and we bring that to focus on the specimen. Recall that when the beam is not focused, All you've done is you've just changed the diameter of that final spot. You've basically defocused it and you've made it a wider beam diameter. Both of those lenses control the size of the fundamental spot from the SEM onto the specimen surface. However, even though the top one, the condenser lens, is called the spot size, the biggest control is with the final lens, the objective lens, or the focus control. Normally, I choose my accelerating voltage to give me the energy I need per electron. I then adjust the condenser lens to give me the number of electrons I need, and then I bring those electrons to focus on my specimen surface. Though, occasionally, I defocus my beam because I want to be gentle on a delicate specimen. But I still need all those electrons landing there, so I defocus and I decrease the energy density on the specimen surface. Variables in analysis. Remember, we're throwing electrons at atoms, and for us, most of the variables will be in the electron beam. 1, the accelerating voltage. This is what you call the KV. This gives the energy or the speed per electron. I need a certain critical energy per electron to generate the X-rays I'm after. So the accelerating voltage, energy per electron, this will dictate which fundamental X-rays I can or can't generate. 2, the condenser lens, first lens down. It's referred to as evidence. The spot size, the probe current, the beam current. It produces the number of electrons. Small spot, few electrons. Big spot, a lot of electrons. More electrons produces more X-rays. I need a certain critical number of X-rays to perform good analysis. The stage, the working distance. The specimen needs to be at a critical height where the X-ray detector is pointed. Even though in an SEM, the specimen can have quite a lot of up and down movement, the detector is expecting the specimen and the X-rays to be sourced at a particular position in Z. And finally, the objective lens. This is what focuses the beam on the specimen surface. Normally, you just focus it to produce the best images and to zoom into a particular particle that you want to analyse. However, for some delicate specimens, I might choose to defocus the beam to spread out the energy density of the beam on the surface. Polymers might be a good example where it's consistent, but I want to be gentle on the specimen. Let's go back to that working distance. What's so important about it? This is a nice schematic through the final lens of the SEM. The electron beam passes through it. We've got our backscatter detector there, and off to the side we have an X-ray detector. The X-ray detector is pointing to a particular position where we can assume the X-rays are coming from. The distance between the final lens and the top of our specimen is called the working distance. With most SEMs we have here at the CMM, we're set up so that your specimen height should be a working distance of 10 millimeters for analysis. There are some other machines and other labs that will be different, but that's typical for us here. In particular, remember the working distance is the distance from the final lens down to your specimen. It's a measurement of the clearance. A working distance of 0 means you've touched your specimen into the lens and you've probably caused damage to the backscatter detector. This is different than Z height, which is how most people think, which is the height of your specimen above the SEM stage. We don't really care how high your specimen is, as long as it's reasonable. What we care is how much clearance we have between the final lens and the top of the specimen, the working distance.